and hope that we don't have any more issues with this silly computer. Okay, so complex 2 is a little bit easier because there's no worry, like there's no coupled proton pumping, so we don't have to think about that. We don't have to worry about that. And in addition, a lot of the chemistry that we're going to see is happening with electron transport, ultimately giving them to iron sulfur clusters, which then pass electrons one electron at a time to ubiquinone to make ubiquinol. So the chemistry really is identical, so we don't need to kind of dive into it. Ultimately, 2 electrons initially come from succinate. They're given to FAD to make FADH2. They're then passed 1 electron at a time through our iron sulfur clusters, 1 electron at a time to ubiquinone to create our semiquinone, and then the fully reduced ubiquinol. Okay, and then the reduced coenzyme Q is released into the membrane, and it can diffuse over to complex 3 called the BC1 complex. Question? Okay. All right, so the BC1 complex, this is another really big protein. Okay, it's a homodimer. It's symmetric. If you look kind of like right down the middle here, it's perfectly symmetric. And each monomer has 11 distinct polypeptide chains. Okay, all this is to say is that the protein is really complex. It has a number of different heme groups, right? We have B-type hemes and C1 type hemes, which if you learned about this, really the only difference is the decorations on your porphyrin. Okay, the only difference between B and C type hemes is what's hanging off of the side. Okay, the cytochrome C unit is up to the top here. So this up here is the matrix side. So this is the cytochrome C unit up here. And then we also have another iron sulfur cluster. This one's called a Reski iron sulfur cluster. And the difference is instead of being coordinated by 4 cysteines, we actually have 2 histidines that are coordinated to one of the iron atoms. That impacts the reduction potential such that it is favorable to move electrons through this iron sulfur cluster, whereas if it was 4 cysteines, at this point in the electron transport chain, it wouldn't be. So all I want you to understand about the presence of the histidines is that they impact the redox potential so that it can be fine-tuned in a way that electron transport is favorable down the chain. We also see there's 2 different types of cytochrome Bs. There's a BH and a BL, which stands for high affinity and low affinity. All this means is that the reduction potential is a little bit different. It is more favorable to reduce the BH than it is the BL. The BH has a higher affinity for electrons. Okay? The overall net reaction is 2 electrons come in the form of reduced coenzyme Q. We're passing these electrons to cytochrome C, which is a single electron carrier. So we need 2 of these. Okay, 2 electrons from coenzyme Q. We give 1 electron each to 2 distinct cytochrome C proteins. We end up with an oxidized coenzyme Q and 2 reduced cytochrome Cs. We pick up 2 protons from the matrix, and we have 2 protons that come from our reduced coenzyme Q to ultimately result in 4 protons being passed into the inner membrane space. So this protein contributes 4 protons being pumped across the membrane. Okay? As it turns out, the chemistry here is not quite as simple as this. This is the net reaction, but the overall reaction involves more coenzyme Qs. Okay? The overall reaction, on our reactant side, we start with 2 reduced coenzyme Qs and 1 oxidized. We pass all of this through the enzyme, and we end up with 2 oxidized forms and 1 reduced form. So the net chemistry is this. One reduced coenzyme Q becomes oxidized. But in the mechanism, we actually see 3 distinct molecules of coenzyme Q involved. Okay, and the reason for this is because we are now transitioning from 2 electron carrier, coenzyme Q, to a 1 electron carrier, cytochrome C. Okay, and instead of using a really simple strategy like having one electron at a time pass through a flavin, or one electron at a time pass through coenzyme Q, this enzyme has evolved to have to use what's known as the Q cycle. Okay, so we're going to walk through it in a couple of different ways. So there are two halves to the Q cycle. The idea is that we have a pool of coenzyme Q. This is going to consist of oxidized and reduced coenzyme Q floating around the membrane of the inner membrane of the mitochondria. Okay, so the idea here is that we bind one reduced form of coenzyme Q in a site called the QO site. So this is like our original binding site. Okay, we pass one electron from our QH2 up to cytochrome C1. This is going through the Rieske iron sulfur center. We ultimately pass it through cytochrome C1, and then we give it to cytochrome C. One electron in the first cycle goes to cytochrome C. We reduce one equivalent of cytochrome C in the first cycle. Okay? The other electron stays with coenzyme Q, and it's given to another, so it's given to this coenzyme Q molecule. It's in this other Q site called the QI site. And this is where our semiquinone is stored. Okay, so one electron goes to cytochrome C, the other electron goes to the QI site where it reduces coenzyme Q and creates this stable radical temporarily in our QI site. We then release one of the coenzyme Qs out to the Q pool. This is oxidized now. In the second half of the reaction, we have another reduced equivalent of coenzyme Q comes in. One electron is given through cytochrome C1 up to cytochrome C. So that's our second reduced cytochrome C product. The other electron is moved down to our QI site where it gives the second electron to the semiquinone, making the fully reduced coenzyme Q. Then both equivalents of coenzyme Q, one in the QO site, one in the QI site, get released to the Q pool. Okay, I'm going to go through this one more time. The first half of the cycle, we have two equivalents of coenzyme Q, one in the QO site, one in the QI site. One of them is reduced, one of them is oxidized. The electrons in the reduced coenzyme Q are given to two different spots. One of them is ultimately given to cytochrome C, and reduced cytochrome C then diffuses away. The other one is passed down to the QI site where it does a single electron reduction of the coenzyme Q in the QI site, resulting in a radical semiquinone. That radical stays in the QI site. The oxidized coenzyme Q then leaves, and a reduced coenzyme Q comes into that QO site. This now is the second half of the cycle. The same thing happens. One electron goes to cytochrome C, reduces cytochrome C diffuses away, goes on to complex 4. The other electron is passed down to the QI site where we fully reduce coenzyme Q in the QI site, resulting in a fully reduced coenzyme Q in the QI site, an oxidized coenzyme Q in the QO site. Both leave. The enzyme is now empty. It can start over. So the overall reaction is two electrons come in from coenzyme Q, two oxidized cytochrome Cs get reduced, but the process by which it happens is more complicated. Okay, let's think about it another way if this helps. Okay, so to kind of align ourselves with this diagram, the left side here is the inner membrane space, the right side is the matrix. We notice here that coenzyme Q is coming into the QO site, and it's coming in from the membrane, right? Because it's embedded in the membrane. It enters into the QO site. It takes one electron and gives it through the iron sulfur cluster, through our Rieske iron sulfur cluster, to cytochrome C1, and then gives it to cytochrome C. The other electron, it passes over to the QI site. And it does this by passing electrons through our two B-type hemes. First to the low affinity, then to the high affinity, but ultimately giving that electron to the coenzyme Q that's present in the QI site, creating the singly reduced semiquinone. Another reduced form of coenzyme Q comes in, binds to the QO site. One electron goes to the iron sulfur protein through cytochrome C1, ultimately to cytochrome C. The other electron gets passed through our B-type hemes. It's given to our semiquinone to result in a fully reduced quinone. Okay, that's the Q cycle. Energetically, the electrons moving from, so the electron that moves from our reduced quinone in the QO site over to the QI site is really at equilibrium. Energetically, there's not much difference in all of these things, but moving it to the risky iron sulfur cluster, moving it to cytochrome C1 and then cytochrome C, that's a spontaneous process. Okay, let's take a couple minutes and work through the second questioning activity.